Okay, so this is a video that's going to finish out the notes that we're talking about today. We're talking about Euler's method and kind of a repeated tangent line process. We went over a graph on how this worked, and now we're actually doing some problems. So kind of fast forward to wherever your class left off, because we're in a different spot in every class, and kind of go from there. So these are the notes that you guys have. So with Euler's method, we're looking at, we need a couple things. The first thing, of course, is the derivative for the function or the equation that we don't know, a point at which we do know that we have a starting point. So that's our number 2 here. Sorry, my differential equation is number 1. Okay, what is it we're trying to truly approximate? So here we're trying to approximate f of 1.4. So that's kind of the fourth thing on our list. And then how many times we're going to partition, or how many steps we're going to make. So that's our number 3 here that we have. Okay, so what we're doing is we're just finding a tangent line at the point that we know using the derivative that we have. So we set up a table and we figured out our change of x. And remember, our change of x came from that formula b minus a over n, where n is the number of steps we're taking. We got 0.2. So we're going to take one step from 1 to 1.2, and then we're going to take 1.2 to 1.4. So this is about finding a tangent line at the point we know to approximate a point that we don't know. So first thing first is to actually get the derivative, because we have the point, and now it's to get the derivative. So all we're doing is we're taking that point and plugging it into our derivative equation. So 1 minus negative 2 minus 1, and when we calculate that, we wind up getting 2. Okay? So we know our slope is 2, which means we can have our or approximate our tangent line, or use our tangent line to approximate 1.2. Okay, so that's going to be our new y value. Okay, so tangent line, all we're doing is we're plugging into that equation that we started with at the top of this page, and it's just our slope, which in this case at this point happened to be 2. Okay, times our change of x. That's our x minus our x1. So 0.2. And then, of course, plus our old y value, which in this case is negative 2. Remember, I'm getting that from that right there. Okay. And then after that, it's just about doing calculations. So 2 times 0.2 gives us 0.4 minus 2, and we get a negative 1.6. So that's kind of the new y value at when x is 1.2. Okay, so now that we've done that, we now have a new point. So we're going to ignore that first point, and we're going to do the same process with that new point that we just found. So because our derivative varies from point to point, we need to reevaluate our derivative. Let me get a thinner pen. There we go. So we're going to take our dy dx, and we're going to evaluate it at that point 1.2 comma negative 1.6. And we're going to plug it in, going back to that equation at where I put a 1 by, and it's just our x value, so 1.2 minus our y value, which is negative 1.6, and then of course minus 1. So when we calculate that, that winds up being 1.2 plus 1.6, so 2.8, and then minus 1 gives us back to 1.8. So here's our new slope. So we're going to take that new slope and that new point and do the exact same thing we did with the first step. So this is our second step. So we're going to take our second step to approximate that 1.4. Okay. So we're using our new slope, which is 1.8. That's what we just calculated a second ago. Our change of x, our x minus x1, so that's 0.2. And then, of course, plus our old y value, which is now that negative 1.6. So what was once our new is now becoming our old. And then we're just doing a calculation. Okay, so 1.8 times 0.2. Guys, remember, decimals can be kind of tricky, so don't worry about the decimals. We're going to do it the way you guys first learned how to multiply decimals, which is you just multiplied the numbers. So 18 times 2, which gives us 36. And then what you did after that, you counted how many decimal places you had in total for each one of them, and then you moved your decimal. So since we have 2 decimal places, we're going to get a 0.36. Okay, and then minus 1.6. When we calculate that, we get a negative 1.24. Looks like it. Okay. And what that means is what we're trying to approximate truly is f of 1.4, and that is approximately negative 1.24. And that's kind of what Euler's method is. It's just really a repeated tangent line approximation where we're using a new point to find another new point. Okay, so that's kind of what it is. So let's do 2 more examples. Okay, let me get to the top here. Well, we can do 3 really quickly. Okay, so it says consider the differential equation. So there's my dy dx. That's my 1. That's the first thing I need. Let y equals f of x. So f of x is our function. Kind of be the particular solution to the given differential equation with the initial condition f of 0 equal to. Remember, f of x is just the antiderivative of this dy dx, which means our point, our starting point, is right there. It says use Euler's method starting at x equals 0, so just reiterating, with 2 steps. So there is my 3 to approximate f of 0.6. So there's the 4th thing I need. So again, what I'm doing is I'm going to do 2 things. I'm going to figure out my change of x, okay, and I'm going to create a table. So our table is going to be x and y, because y is going to be our tangent line, f of x is our function, and we're going to use 0, 2, okay, and we're going to use that to approximate 0.6 on our table. So our end point is 0.6, our start point is 0, and we're going to go 2 steps. So that just winds up being 0.6 divided by 2, which is 0.3. So 0 plus 0.3 gives us 0.3. Like, duh, like we know that. That's kind of a simple one. Okay, now once I have all of that information, now it's time to start using that point that we know, that 0, 2, and figuring out what our dy dx is at that point. Okay. So I'm going to evaluate. We're going to evaluate it at 0, 2. And all we're doing is plugging into that dy dx is equal to x minus 1. So 0 minus 1 gives us negative 1. So there's our slope. Then we're going to use that to find the tangent line and use that to approximate the next point, so our first step. So our y of 0.3 is going to be our slope, which happens to be negative 1, times our change of x, which is 0.3, plus our current y value, or our old y value, which happens to be 2. And we're just going to calculate what that is. So we get negative 0.3 plus 2, which gives us 1.7. So this right here is 1.7. So then we're going to do that same process again. We're going to take our slope. We're going to figure out what that is. I'm going to do that right here because I'm running out of room. I apologize. And we're going to evaluate our slope at that point 0.3 and comma 1.7. Okay. So all we're doing is plugging in our x value, 0.3 minus 1. And 0.3 minus 1 gives us negative 0.7. Going back to plug in, okay, we're now calculating y of 0.6. So our new slope is negative 0.7 times 0.3, that's our change of x, okay, and plus 1.7. Okay, so now we're just going to do a calculation. 7 times 3, 21. That gives us 0.21. So that gives us negative 0.21 plus 1.7. And when we calculate that, we get 1.49. which means our f of 0.6 is approximately 1.49. Okay. Let me make sure that I did not make a mistake anywhere in this process. Okay, so it looks good, so we're going to go with it. If I made a mistake, please double check my work and then kind of point that out to me when we see each other again. Okay, so the next one. Now the next one, what I noticed right off just by looking at the information is that my dy dx is actually a fraction. So this may be one of those ones that we don't want to put in decimal form. That fraction form may actually work better. But we're going to kind of see when we go. Okay, so I'm going to start in a fraction form, and if we need to go to decimal form, then I'll do that as I'm going. Okay, but traditionally, fractions, decimals, whichever one you feel more comfortable working with, that's the one you should really work with. Okay. So first things first, I have my derivative, which is right there. Again, if I can get my pen to work, you know how that is. And y of 0 is equal to 1. So they have defined my function as y. And I don't want my tangent line and the function that I'm dealing with to have the same name. So I kind of want to distinct. So instead of using y for my tangent line, I'm actually going to use t. Okay, I'm going to pick a variable, t for tangent line. So I'm going to use t of x, and I'm going to declare that to be my tangent line. That way I can keep those two things straight. Okay, I don't want my functions being named the same thing because that can get confusing. Okay, so when I create my table, I'm not going to have x and y, I'm going to have x and t. Okay, and sometimes our tangent lines are actually named t of x. So that's kind of one thing. And my starting point, which is 0, 1. And I want to get 2, so that's my 2, what I have, to find the approximation of y of 1, so that's my 4, using 2 steps. That's my 3. Okay, so I know I want to get to 1. Okay. So that means my change of x is my endpoint minus my start point over the amount of steps, which gives me 1/2. So I'm going to leave it as 1/2. Okay. Now it's about figuring out what our dy dx is. So that's where I'm going to start now. So my dy dx, use my pen, evaluated at 0, 1. That's the point that I know right now is going to be equal to 1 over 1 plus 2, which winds up giving me 1/3. There's my slope. So now it's about finding my tangent line. So the first thing I'm going to do is to get t of 1/2, and that starts with my slope, so 1/3, times my change of x, plus my y value, which happens to be 1 here. So then I get, multiplying our fractions, we get 1/6 plus, and I'm going to turn that into a common denominator right now. So we get 7/6. Okay, so 7/6. Okay. So now we're on to our next one. Again, I'm going to reevaluate my derivative, and we're going to evaluate it at 1/2, comma 7/6, that new point. Okay, so 1 over our x value, which is 1/2, plus 1. That is ugly. I do not like that. So we're going to get 1 over 3/2, which turns into 2/3, multiplying by the reciprocal. So just doing some work with fractions. Not bad. Okay, so now we're going to use that new slope, t of, to find t of 1, or to estimate t of 1. So we have 2/3 is our slope, Our change of x was 1/2. That's consistent. And we get 7/6. Okay. So how nice is that? We wind up getting 2/6 plus 7/6, which gives us 9/6, which reduces to 3/2. Pretty nice. That kind of worked out nice for us. Interesting. So even the fractions were not a big problem in this one. So what that means for us is that our y of 1 is approximately 3/2. And there we have it. Okay. Now the last example is an example that is in table form. I don't like table form. I'm used to my types of tables. So the first thing that I do when I see a problem like this is I go back and rewrite it just exactly the way I would any problem. The thing that benefits us here is that our derivative is already calculated for us if we see that middle line, which is nice because that's one less thing that we have to actually calculate by hand. So I'm going to create a table, and I'm going to take this and x and my y, just like I did in the previous problem, and I'm just going to extract the stuff from the table. So remember that this is my x, this line right here, and these are my y's. The in between, that right there is our dy dx. Okay, so we're extracting our point, so our point is 3,2. And we're just going to do this process just like we did before. Our dy dx at 3, so our dy dx, and I'm just pulling the information from the table, at 3,2 happens to be 0.4. Okay, so I'm just pulling that information from here. So now we're trying to estimate the 2.8. So our y of 2.8 is our slope, which is 0.4. Now the only thing we didn't do is our change of x, but if we look at our table, our change of x is kind of pretty clear. It's actually a negative value, so we're going down in value. So if we think about our change of x, 2.6 minus 3 over, and we're doing 2 steps again. So if we get that, we get negative 0.4 divided by 2, which gives us negative 0.2, which is kind of easy to see from the table, but here's the calculation for it. So our slope right there of 0.4 times negative 0.2 plus our y value of 2. So let's calculate that really quickly. We get negative 0.8 or 0.8. Sorry, negative 0.08, because 4 times 2 is 8. Move the decimal over twice, and that's why we get that 0.08. So plus 2, which means we get a 1.92. So that's our new point, a 1.92. So at 2.8, and I'm kind of doing double work here, but that's okay. This is a way to keep myself organized. This is what I'm used to. I get that. Okay. Now we're done with this one, so we're on to the next one. So our slope there winds up being 0.7. So now to calculate y of 2.6, I start with my slope, which is 0.7. That's coming from that middle block that's not highlighted out, times my change of x, which is negative 0.2, and then of course plus the 1.92 from the point that we just found. And then we're just doing calculations. So negative 0.14, 7 times 2 is 14, move the decimal over twice, plus 1.92, and when we calculate that, we wind up getting 1.78. And what that means for us is that f of 2.6 is going to be approximately 1.78. Okay, so that's Euler's method. Remember, there's 3 things I wanted you guys to work on: your FRQ, finish out these notes, and then if you have time, start the practice that starts on the next page. If you guys have any questions, come see me Monday morning, and have a good weekend.